So, hi everyone. It's good to see that many of you are here despite the exercise deadline today. Before we start with the lecture, as usual, some organizational announcements. So I contacted all the teams that are planning to do a seminar at the end of the term and asked about conflicts that we should take into account for the scheduling. I haven't received much feedback so far, so only 2 groups told me their preferences. So I assume the other groups are fine with any of the 3 slots that we reserved at the end of the term. If you still think of any conflicts, please send us to them right now. Otherwise, we would fix the schedule for the last 3 lectures right at the end of the of this lecture unit here, and we'll send you an email with the detailed seminar talk titles. Okay, so now for the lecture. The topic for today is a sort of continuation of what we've been doing in the last 2 weeks. But today we are going to look not at the theory background, but at some tools that will help us achieve the things we've been talking about in the last 2 weeks. So in particular, we are looking at automated tools that are useful for performing statistical attacks like linear and differential cryptanalysis. So the plan for today is to first have a few general words about computer-aided cryptanalysis and the role that the computer usually plays in what we are doing. Because you may have noticed that many of the papers that are published are mostly pen and paper stuff and don't really seem to involve a computer. And we will spend most of the lecture looking at 4 very different tools that have been successfully applied in the context of finding differential characteristics. Most of them are so general that they could also be used in essentially the same way for finding linear characteristics and even more general cryptanalysis goals. So the 4 methods that we're going to look at 2 we're going to look at in more detail, and at 2 just very briefly. So the first one, Matsui's branched and bound algorithm, is a general algorithm that has been suggested very early on by the inventor of linear cryptanalysis and has been used to find differential trails for DES. And we will quickly look at this algorithm, but also see that for modern ciphers, it's not really applicable or efficiently applicable very often. For this reason, we are going to look at 2 general purpose tools, which are sort of automated solvers for general problems, which can be adapted quite nicely to cryptanalysis goals. And those 2 are going to be mixed integer linear programming, which we're going to look at in some detail, and then Boolean satisfiability and constraint programming, which we're going to have only a brief look at, because this Boolean stuff is both related in some ways to the MILP approach and in some ways to the 4th method that we're going to look at, which is a general, a dedicated search tool, which was programmed specifically just for the goal of looking for differential characteristics. But the underlying ideas are quite similar to SAT solvers, which is why we don't go into too much detail on SAT solvers. Okay, so this is the outline for today. Let's start with a few general words about the role of computers when doing cryptanalysis. So you may have noticed, if you've been looking at some of the attack papers that we have linked throughout the lecture, that many of the attacks that we've been talking about are mostly presented as pen and paper stuff, and actually most of the details are verifiable by just doing pen and paper stuff as well. So just by reading the attack description and thinking through the claims there, you can verify that this is an attack that should probably work and that should have this and that complexity. And the reason why many of the stuff that we've been looking at has this theoretical nature is that the attacks that we usually publish are typically round reduced attacks on rather good ciphers, which also means they're good ciphers, so they're relatively strong against attacks. And this means that many of the attacks we're interested in have a very impractical complexity, so they are too high to actually execute, at least if you're working on a university budget like we are. And the reason for looking mostly at attacks with impractical complexity is because these strong attacks usually do allow us to derive some information about more efficient versions of the attacks on fewer rounds, for example, of the cipher. But since we're trying to be defensive or conservative in our analysis. We try to make sure there are no attacks, so we should look at the strongest attacks possible, or on those covering the highest number of rounds, even if the resulting complexity is pretty high. Because what we usually are trying to do is we are trying to overestimate rather than underestimate the attacker. If we overestimate the attacker, the worst thing that happens is that we have a bit too many rounds in the cipher or so it's a tiny bit less efficient to execute. But of course, it's much worse if we underestimate the attacker. So we usually drive this to the margin and consider attacks with the highest complexity that is still below some security bound or so. But that is in any case too high to actually execute. There are of course also some papers that do look at practical attack complexities. For example, because they actually recovered the keys of some car keys or something like that. But these are usually cases where the underlying ciphers are really crappy. And the good thing is that we don't have too many of those. And in particular, once one attack on such a cipher is published, nobody else will probably have a look at it. Whereas on good ciphers, we have more and more cryptanalysis to get a better and better understanding of their security margin. So this is part of the reason why much of the stuff we are looking at is limited to paper considerations, because the complexities are too high to actually carry out. However, there are still quite a number of things where we do need computers. The first of them being the experimental evaluation of parts of the attack. So even if the full attack is too expensive to execute, it usually relies on a number of statistical assumptions, like a Markov assumption or an independence assumption. And verifying these assumptions is very crucial because in some ciphers they may not actually be satisfied. So to gain some confidence whether the theoretical complexity estimates are actually okay, we usually need to do some experiments that execute only a part of the attack or on a smaller cipher or so, but still something that needs to be carried out and that does have some computational complexity, which cannot be done by hand. Another reason why we do need computers is, of course, ciphers are designed to be complex. So some of the problems we are facing there are simply not feasible to solve by hand, but they are feasible by somebody who can compute faster, meaning our computers. And this is in particular the case for tasks such as finding a differential characteristic, maybe finding some actual attack or executing some actual attacks such as collision attacks practically. This is where computers can help, and this is what we are going to look at. Another thing is that not only ciphers are designed to be complex, but designing ciphers is also complex. And when we do this, we typically want to choose the individual building blocks in the best possible way from some design space. So for example, we're choosing an S-box, which we want to have to satisfy certain properties. And what we can do is we can use tools to search through the design space and select some of the best building blocks that we can find in there. And since these spaces are usually quite large, we also need, again, a computer's help to do this. Okay, so these are sort of the quick overview about where we could use a computer and where we usually don't. So the short summary is probably there is actually quite often a computer involved at some point, but this doesn't always show up in the papers. Or if it does, it often does only briefly, such as, oh yeah, we verified this and it works. Or we found this differential characteristic. Here it is, please verify that the probability is okay, but you couldn't easily find another similar characteristic, because for this you would need a computer. But you can verify the characteristic using just pen and paper. So what are some examples of specific parts of attacks that can be done with the aid of a computer? In linear and differential cryptanalysis, the typical thing that we do use a computer for is for finding good characteristics that cover a large number of rounds. For few rounds, such as we had in the exercises in Applied Crypto 1, it's often feasible to do this by hand. So for 1 or 2 rounds, it's often pretty obvious which characteristics are good and what they look like. But for more rounds, this is not the case. Another thing is for proving that the characteristics we have are actually the best possible ones. So we want often to prove bounds that there is no characteristic with a probability higher than some bound that we're interested in. And for this, we also may need the help of a tool. And finally, for attacks that aren't like the classical key recovery attacks, but that are sort of one-time attacks, which you execute once and then you get a result and that's it, such as collision attacks, we also sometimes need a computer to find the actual values of a collision. If we look beyond this, these classical attacks and look at more advanced attacks, then we see that these advanced attacks often combine partial attack fragments from different strategies. So for example, in an impossible differential attack, you often combine two incompatible differential characteristics. Or in differential linear attacks, which you will hear about next week, I think, briefly, you also try to combine a linear characteristic with a differential characteristic. And to find such combinable fragments, tools are also often quite useful. And finally, there is quite a different class of attacks which we haven't seen yet in detail, but which we will also have a lecture about, and that is algebraic attacks, which are more about solving equations. For example, for recovering the key, or also for finding algebraic properties that hold over many rounds of a cipher, such as cube attacks or a division property. But since we haven't covered the theory for that yet, we are not going to talk about it much in this lecture, and instead we are going to focus on the first part here, so on linear and differential cryptanalysis, and in particular on finding good characteristics for many rounds. Okay, so what tools do we have, and what choices are there, sort of, or what do they have in common? So finding characteristics is definitely something that can be hard, but it's also definitely something that we need both as a designer, because we want some bounds, and as a cryptanalyst, because we want some attacks. Now, some ciphers do manage to do this by carefully designing the cipher and making it possible to do by hand, such as the AES. But in most cases, this is not possible, and we need to use some tool. Now, these tools usually consist sort of two parts. One is the actual solver that takes a well-defined problem in a particular language and finds a solution for it. And the other part is matching the crypto into something that matches this model. And for this reason, we usually distinguish two types of solvers. So the one is general purpose solvers, such as sub-solvers or MILP solvers, which can process a quite general language or class of problems, and which are thus used to solve all kinds of problems, from biology to physics to crypto. And this means that most of the work that the cryptanalyst needs to do is translating the crypto problem into a problem that can be understood by such a general solver, such a general purpose or off-the-shelf solver, which means that the hard programming work of efficiently implementing the solver is done by somebody else, and just the translation part is our task. And the other category is dedicated solvers, which means that we essentially don't use any third-party stuff or any existing solver, and instead we do the hard work of writing the search procedure, of designing the search procedure. The advantage is, of course, that we can define the search procedure exactly for the language we want to look at. So for example, we can specifically model it for the language of differential cryptanalysis and finding differences. So we will have to spend quite a bit of effort in writing the solver, but then the translation from crypto to the solver will be quite easy. And we can also often use some domain-specific knowledge from crypto in order to make the solver more efficient, and to use some of the things we know from cryptography to make the search more focused or faster. Look at the more relevant things first. And this modeling that I described, this consists of several steps. So the first of these is that we usually need to model some sort of constraints which characterize what we're actually looking for. So in our case, we're looking for differential characteristics. So we somehow need to describe which differential characteristics are actually valid. Valid here meaning it doesn't have probability 0, but it has some non-zero probability. Or in the linear case, it would mean a linear characteristic that does have a bias. An unbiased solution would not be useful. So we need a way to characterize which characteristics are okay, which can be done on different levels of granularity. So in some solvers, we usually do this in a more coarse-grained way. So for example, we look at truncated patterns. We are only looking for a pattern of which S boxes are active, and we don't look at the actual specific differences that are there at the input of the S box. This is, for example, what we do in AS-like ciphers. And in some cases, we want to have a more fine-grained description. So we really want a precise definition of which bitwise masks or bitwise differences we can use in each round and which combinations are valid. So modeling what a valid solution looks like is the first and most important part. But what we also often want to do is we want to somehow model the cost of a particular solution. Since we are looking for the best possible or a very good characteristic, we need to somehow define what the cost of a characteristic is. And in some languages, this is very easy to express, and in others, it's rather painful. And finally, we want to settle what our actual goal is. So do we just want to find any solution or a good solution? Do we want to find all existing solutions with some particular constraints? Do we want to find the best possible solution, and so on? So of course, finding the best solution, for example, is nice, but it's not always feasible. In some cases, we need to be satisfied with just finding one reasonably good solution. Now let's look at the first and maybe most classical approach for finding such a characteristic, which was introduced by Matsui, the inventor of linear cryptanalysis, and was also published quite soon, like a year or so after the invention of linear cryptanalysis. And it was first used to find the best possible characteristics for the block cipher DES, which was also the original target of linear cryptanalysis, as well as differential cryptanalysis. And this is an approach that works both for linear and for differential characteristics. And if we'd like to characterize it, I think the best way to do so is to say that it's a dynamic programming technique that tries to build the best possible characteristics round by round. So it starts with finding the best solutions for few rounds and then keeps extending them, but in such a way that we always get the best solution for all rounds, and not just we take one best solution for fewer rounds and then try how we can best expand this, because it might always be possible that there's a better solution for a worse solution for the first few rounds that then can be combined in a better way for the last step. So we still need to make sure that we always really get the best one. And to do this, or to make this reasonably efficient, we usually consider two numbers in the search. So one of them, the BI, is the actual best differential probability for I rounds. So this is illustrated in the figure on the bottom here. So B1, B2, and so on up to Bn denote the probability of the best possible characteristic for this number of rounds, where the deltas here are the individual differences after the first round, after the second round, and so on, and R is short for the round function. And in addition to this actual optimal solution which we are looking for, or this best possible value, we are also always carrying along a bound for the solution. So this is a lower bound which is guaranteed to be at most as good as the best characteristic. So it may not be. For an example for what we could use here is the probability of some characteristic that we found. Now the some characteristic is not necessarily the best one, but it does have a probability that is most as good as the best one. And notice that we are just looking for the numbers here. We are not yet looking for the actual characteristics. These will be constructed along the way and we will know them at the end. And the idea is now to derive the best, so to do a sort of induction and derive the best probability for n rounds, for knowing all the best probabilities for I rounds where I is at most n-1. So we first, we do this inductively, starting here, then the best probabilities here, then the best for 2 rounds, and so on. And how do we do this? So it works both recursively and inductively. And if you want to show that it's correct, you can do this by an induction over the number of rounds n. And for this, we first initialize the bound b, so this b bar. For this, we can simply take any starting characteristic. We can do this, for example, by taking any input difference, then finding the best way to extend this input difference for one round, remembering it for b1 bar. Then we can, starting from this fixed difference, find the next best transition for the next round, and so on. And we do this up to n rounds. And then for any number of rounds, we have one possible solution. And the probability of the solution is always the best one that we found up to n-1 rounds times the probability of the last round that we are adding. And now to find the actual optimal value, of course, we cannot just consider this one characteristic, which we did in a sort of, we built this in a sort of greedy way, always just looking at the one next step and taking the best possible next step. But we don't know anything about the global optimality of this. So to find out something about the global optimality, what we're trying to do is, essentially we want to build a recursive search that would originally cover all possible characteristics. So starting from each delta 0, we are looking at each delta 1 and combining each delta 1 with each delta 2 and so on. So we would get a huge tree, which we definitely can't enumerate. But what we try to do is we try to cut off early all the branches that will not lead to a characteristic with good probability. And to find such an criterion and to decide whether a characteristic can possibly extend it in a good way, we can take the bounds that we have found so far. So based on this lower bound here, we can see for any partially built characteristic that we have so far, we can see that if we assume that starting from delta 1, we can extend it in the best possible way, if the resulting probability is then better than the bound we know for n rounds, then this could still be promising. It could still be possible to extend this to something useful. If, however, the cost, even assuming the best possible extension of the current partial characteristic, if even that is not better than something we've already found, then this is not a promising branch and we can throw it away right away. And so at each step we consider, or we keep only the partially built characteristics that could potentially still be completed to something better than the current bound, and the rest we throw away. And so for each promising combination delta 0 and delta 1, we recursively try to do the same thing for combining this with any delta 2 that we can find. And again, we always try to evaluate the rest of the branch based on assuming the best possible for the rest of the rounds. And if it looks promising, we keep it, otherwise we throw it away. And we continue doing this until we have reached the full number of rounds n. And whenever we have reached this full number of rounds n for any complete branch, of course, we can also update the bound we found so far, because if everything here worked as expected, then the characteristic we found is at least as good as the previous bound, so we can update the previous bound with this potentially better bound, which means we can cut off the following differences even sooner. So this is the general approach. Of course, you can see already here from the definition of these loops here that this looks pretty expensive. So for example, here for the first step, we're already supposed to combine every possible difference for the first round with every possible difference for the second round. So this is the state size squared in terms of complexity, which if you think of something like AS, definitely does not look promising. So this means two things. First, it means that we should not just stupidly implement this algorithm, but we should think about which cases we can already exclude beforehand before even evaluating all these combinations. So for example, if our starting difference already has a fully active state or so, then maybe we can already exclude it beforehand and see that this will not lead to anything useful. So we need to start thinking and pruning the things we're looking at even before we actually start evaluating the combinations. So this means some extra programming effort. The other aspect is that this is still pretty infeasible if our so depending on how strong or how modern the block cipher is. So if the block cipher has a large state and it has a very good diffusion and very low probability characteristics, then this will still not be practical. But in the case of DES, where the state size is only 64 bits and it's a Feistel cipher, so actually we can look at the Feistel halves separately and just always consider the 32-bit new difference that we get each round, then each of the deltas is suddenly only 32 bits large. And additionally, the individual characteristics have a relatively high probability, which means we can already exclude many candidates early on. So this makes this approach feasible, for example, for DES or something like that, but rather hard to apply to most modern ciphers. But still, it's sort of the original attack approach, and it still has many applications. And people have also tried to adapt this approach to newer ciphers or to new design strategies. So, for example, to ARX ciphers, which we'll also encounter later on. Okay, so in summary, a nice and very general approach, but it's in many cases too inefficient to actually execute. And it also needs quite a bit of extra thinking by the programmer to implement this cleverly. Okay, so this is already the first method. I won't say much more about it because it doesn't play that much of a role in typical recent designs. So let's instead, let's briefly summarize what the properties are, and then let's look at the next method. So to summarize, this is an algorithm that does solve an optimization problem in the sense it really guarantees to find the best characteristic. And it does work well when there are not too many candidates to test. So exactly what we just said, a small state, few good characteristics. So a lightweight Feistel cipher might be an ideal candidate for this. What's also nice is that even if you can't execute it for a full number of rounds, you can, for example, apply this algorithm to round-reduced versions and then multiply the results you get for partial rounds to get at least a bound for the best probability. But for modern ciphers, this is not really feasible, and it's also hard to adapt to many more recently popular concepts like related key characteristics or related tweak characteristics and so on. On the other hand, a recently much more popular approach is so-called MILP solvers. So MILP is short for mixed integer linear programming, which is in turn a generalization of linear programming. So linear programming is a method and language for solving a particular type of optimization problems, namely one that's all about linear optimization. So what does this program language describe? First, the variables that we are working with, so the decision variables that we are going to want to find a solution for, these are originally real valued variables. So real valued positive variables, which doesn't sound a lot like crypto, so we will get to that in a moment. The optimization goal that we want to solve in linear programming is always a linear objective function, which can be minimized or maximized. And linear means it can be written as some vector of coefficients times our vector of variables, or in other words, the cost function is always a weighted sum of our decision variables. So for each of the decision variables that we have, we can apply a weight, linear weight, and then we sum the weighted values. So this is what we can optimize with this sort of tool. And now, of course, we also need some constraints, otherwise this would be too easy. And these constraints also have to be linear, meaning each of these constraints is also written as some weighted sum of my decision variables needs to be below some bound. So in general, we also write this in a sort of matrix times vector multiplication, where the matrix describes the constraints, the x is the decision variables, and b are the bounds for each of these linear equations. So in total, we can very briefly summarize what a linear equation system or a linear programming system is. It's a maximization or minimization problem that maximizes over all decision variables in this d-dimensional real space. It maximizes this linear function ctx. T simply means we are transposing this vector here, so it's an inner product. And this is under the constraint that some matrix times my decision variables is below some bounds, and all the decision variables are positive. Now, of course, you can also write down equations such as some linear combination needs to be larger than some bound. We can simply do this by adding a minus sign on all sides and then turning it back into this format here. Similarly, there are also a number of tricks like working with variables that are not necessarily positive and so on. So there are many small gadgets or tricks so that you can write more general equations with this. But in short, this is the general format that is accepted as an input by these tools. Now, this by itself doesn't really sound like crypto at all. So first of all, the things we're looking at usually don't look so linear. And second, we are usually certainly not working with real valued variables. Now, the good thing is that there is a generalization of linear programming that is called mixed integer linear programming, which allows that some of these variables are constrained to integer values, which means some of the x variables are still real numbers, and for some of them we can require that they are integers. This already makes the whole thing a lot more attractive for us. The bad, here's an example, by the way. So this is an example over a two-dimensional space of candidate variables, so x and y. So x and y correspond to the indices of this x here. And in this example here, we have three constraints which are marked in green. So each of them has the format that some linear combination of the decision variables is below some bound. And actually each of these constraints corresponds to a so-called half plane geometrically. So in the two-dimensional case, this is a line, but in 3 dimensions, this would be a plane that cuts the space of all variables in two, and everything on the one side is okay and everything on the other side is not okay. So here I've always drawn the limiting line that is defined by these equations, and everything on the side where I've written the equation is okay. So this line says that all variables in this half of the space are okay. This one here says that everything below here is okay, is permitted by the constraints. And same here, everything on this side. So everything in this thing here with 5 angles or 5 corners is an acceptable solution. And now we have a maximization goal. What we're wanting to maximize is the sum of x plus y. So this maximization always gives us a direction in which the values are getting better. So in this case, the direction is this one here. So everything on this line here has the same cost, for example, and everything below it has a lesser value and everything above it has a better value. So we want to go as far in this direction as possible. And in this present case here, that is exactly this corner point here. And this is actually not by accident that the result is a corner point, but in fact the optimal solution in such a problem is always a corner point, which means that they are very, very efficient for finding these optimal solutions, at least in the LP case, where LP was where everything is allowed to be a real value. Because of this, of course, this coordinate here, this is not an integer value. So if we now add integer constraints and we say that our solution has to be an integer, then only the points marked here in gray are acceptable solutions. Among these, the best one is this one here, because it's the farthest in this direction. However, this is no longer a corner point, which means it's much harder to find. Which also means that solving an LP problem is in fact a lot easier than solving a MILP problem. And solving a MILP problem typically gets harder the more integer values there are. This is because of the way that this integer condition is handled internally. which also does this sort of branch and bound like we've seen in the Matsui algorithm, but in a slightly different way. Okay, so this is what such a problem looks like. Of course, we are not going to be limiting it to something nice and two-dimensional that I can print here, but we are rather going to have a dimension in the thousands, for example, or in the example that we are going to look at, it's at least in the hundreds. So on the hardness, as I said, LP is easily solvable. MILP, unfortunately, can be NP hard. There are still some well-known tools which are very, very good at solving this type of problems, and two of the most well-known ones are Cplex by IBM and Gurobi, which was started by some ex-engineers working on Cplex. So both of these have academic licenses available, but they are not fully open source or fully free. So you can use them, but yeah, with a sad eye and a happy eye. There are also some completely open source solvers, but they are unfortunately a lot less efficient than these. Now these solvers can either be used standalone, meaning they accept a particular input file format which describe exactly this sort of input format. So in the sense of it accepts a matrix A and a bound B and so on. But it's also available in much more convenient interfaces as libraries in several different programming languages. So the way we usually use it is via Sage or C++, or sometimes as a sort of mix of the two, because some of these interfaces can also generate these LP files to feed to the standalone solver. So let's have a look at a crypto example and how we are going to model it in this strange format. So for simplicity, we are going to look at AES, which was actually one of the first ciphers where this was proposed. And our goal is going to be to find the best possible truncated patterns for characteristics. So this picture here should look familiar. This shows a pattern of active S boxes or active cells for AES across the operations subbytes, shift rows, mixed columns, and the key addition. And we see already here the good diffusion effect that AES has, because this single active cell in the input quickly goes to 4 active cells and then even a full 16 active cells after only 2 rounds. And this is actually quite a typical division in MILP, that we first use a MILP solver to find the sort of pattern, the best possible pattern. And then afterwards, we are trying to find an actual selection of differences that satisfy this pattern, or alternatively we just use this pattern to derive a bound. So for example, we know that each S box here has a probability of at most 2 to the minus 6. So if we know that the best pattern has in this case 5 active S boxes marked in red, then we know that the best possible probability is 2 to the minus 6 to the power of 5. So this pattern can either be used for bounds or for finding actual solutions. So this is an example of an actual solution for, well, almost for this trail. I just see that I switched the columns, but yeah, whatever. I think you can imagine how this adapts otherwise. Okay, so this is going to be our goal, finding such a thing and describing the possible patterns here with the help of the MILP language. So let's have a look. Let's first see what our decision variables are. So what we want to know is, for each cell that is involved here after these rounds, we want to know whether this cell is active or not. So whether there is a difference here or there is none. So this sort of suggests that we should maybe use one variable per state cell here. So 16 variables for the first state, another 16 for the next, another 16 for the next, and so on. And each of these variables should be binary, where 1 means the cell is active and 0 means the cell is not active. So this is a good start. Now the question is, how do we describe which transitions are actually possible? So the first operation we're going to look at is the add key operation. Now this is actually quite easy, because for now we are just going to assume that the key doesn't have any differences. So we're never adding anything here, which means if you take something that has a difference, add the same constant to both of them, then afterwards there's still going to be a difference. So in other words, the input pattern and the output pattern for the add key need to be exactly the same in a valid characteristic. Let's next look at subbytes. In sub-bytes, if we have an input pair with a difference between them, then naturally, since the S-box is a bijective function, the outputs must also have a difference. There cannot be a collision in the S-box because different inputs always generate different outputs. So for sub-bytes, all possible patterns must also have exactly the same pattern here and here. It needn't be the exact bitwise difference here, but so far we are not looking at the bitwise difference. We're just looking at the pattern. And the pattern needs to be the same for both. Additionally, S-box is also where the cost comes in. So each active S-box here sort of adds to our cost. So it would be a logical way to say that the cost function is simply the sum of the S-box inputs here. So for example, in this case, the sum is 1 because just one cell is active. In this case here, the sum is 4. So our cost function is going to be exactly the total number of active S-boxes. So what about shift rows? Shift rows simply swaps around the position of the active bytes. It doesn't really change anything about the difference. It just changes at which position the relevant cells are. So we can do this by a simple variable renaming. So each variable here corresponds or is exactly equal to some variable here. Which one depends on what exactly shift rows does. But this is trivial to do. And finally, mixed columns is the most interesting one. So when is the transition to mixed columns valid? Now for AES, the good news is that this is very easy to answer. So we do know one condition that definitely has to hold for mixed columns. We said that mixed columns is such a magic MDS matrix. So a perfect matrix where if we have only one active input cell, it always gives us 4 active output cells. For 2 active input cells, we get at least 3 active here and so on. So it has a so-called branch number of 5. What this means is that if we sum the cells here and here, then the sum must be either 0 if mixed columns is completely inactive, or it must be at least 5 because this is the branch number. So in other words, for each active column, the sum of the inputs plus the sum of the outputs must be at least 5. Now, so far we know that this is a necessary condition. It could potentially be that some of the patterns that satisfy the condition are not possible. So for example, it could be that if these 2 are active, it's not possible that precisely these 3 are active, but maybe only some other 3. But for AES, this is actually not the case. So in AES, this is actually a precise description of mixed columns. So any pattern that satisfies this is valid, and vice versa, any valid pattern satisfies this, this condition here. So this is a perfect description of mixed columns, which is remarkably simple and which looks exactly like the format we want to have. The sum of some variables plus the sum of some variables is bigger than 5. This is exactly the sort of constraint we want. So it turns out that even though AES is generally very complex, the patterns that are possible are very easy to describe. So let's write that down in maths. So we will need variables so in each round R, we're going to need 16 variables where I goes from 0 to 3 and J goes from 0 to 3 and denotes the row and column in this state. And each of these variables is going to be binary. So where 1 means it's active and 0 means it's not active. And additionally, we are also going to need some helper variables, which are relevant for this last step here. We said here, this condition must be for each active column. So we are going to use a helper variable for each column in each round that tells us whether mixed columns is active in this column or not, where active means any of the inputs is active. And then we can describe what we had on the previous slide as follows. So what we want to do is we want to minimize the number of active S-boxes. In other words, we want to minimize the sum over all rounds, over all rows and columns of this variable Srij. Notice that we only took variables not just for every state like we had in the previous slide, but just for the red boxes here. So in our model, we only have variables for the red boxes and for the columns here, for the total columns. And we're going to optimize away all the rest because we saw for add round key, the pattern doesn't change. We can use the same variable here and here. Here, the pattern doesn't change. We can use the same variable. here the pattern does change, but only by moving them around. So we can simply use a reordered, permuted version of the variables before and after this here. And the only thing where it changes is here, but this is again the same as the next step. So we actually only need variables for the red stuff here. And we're also only counting the red stuff because this is exactly the cost. So what are our constraints? We have one constraint for each mixed columns, which says that the sum of the input values, you will see that they are mixed around here due to shift rows. So the sum of the input values to the mixed columns plus the sum of the output values, which are simply the S-box inputs of the next round. This sum here needs to be, we said it needs to be at least 5, which is the branch number. However, this condition only needs to be satisfied for active mixed columns. So what we can instead write is we can write that the sum needs to be larger than this constant here times our mixed columns variable, which means if mixed columns is not active, then this here simply says then sum needs to be at least 0. Well, this is not a condition. And if mixed columns is active, it says it needs to be greater than 1 times 5, so greater than 5. So this is great. What we still need to make sure that this assignment also works vice versa. So we need to guarantee that M actually turns to 1 when mixed columns is active, which is what the second half of this condition is for. So we're saying that the sum can be at most 8 times the activity. So if any of these is active, so the sum is at least 1, this can only be satisfied if M is also 1, because if M is 0, then this here is 0, and this would be a contradiction. I hope this makes sense. So in total, you see that I'm writing things shortly here. I squeezed 2 constraints into one line here, but we simply write this down for every round, for every j, and here the sum is over all i's, over all rows. And finally, there's one extra constraint which we haven't talked about yet. The thing is, if I put just what I've written so far into the solver, what would it give me as a solution? Well, it would give me the cheapest possible solution, which is to simply have everything set to 0. This is definitely a valid characteristic according to our description, if all the differences are 0. However, it's a characteristic or a pattern that is not really useful for us because it's a trivial characteristic. We need that there is at least one difference so that we can do any attack. So for this reason, we add the last constraint here, the so-called non-triviality constraint, which says that in the first round, there needs to be at least one active cell. In other words, the sum over the cells needs to be at least 1. So this is the math description. This ST here is short for subject to or such that. So meaning here the constraints start. We can also write this down in code, and it's not much longer than this. So this is a complete implementation of the previous problem in the MILP interface that you can find in your Sage. So you can, if you have Sage installed, you can run this right away. And it will use an inbuilt MILP solver, which is open source. So I think the default is CoinOR, but I'm not sure. Which is a lot less efficient than the others we've talked about, but it's still by far enough for this sort of problem because this is actually a very easy problem to solve. So how does the code look like? There's one variable here that is the number of rounds. So in this code snippet, this is for 4 rounds. We say we want to create a new mixed integer linear program. Here you say whether you want to maximize it or minimize it. In this case, we want to minimize. Then you can add variables where a variable is actually a vector of variables. So if we say we have a new variable s, then we can actually later use s indexed with anything we like. So in particular, we can index it with our round number, our row number, and our column number later. So s is for the S-box values and m is for the mixed columns activity. We don't have to specify in advance how we are going to index it. It's going to be a large set that is accessible with any tuple. And we say that both of them are binary variables. So this is setting up the program. Now we're describing the constraints. We said that the constraints are for each round, for each column, we have this mixed columns constraints. So the active cells need to be at least 5 times mixed columns activity and at most 8 times mixed columns activity. And the sum I've written down here. So this is the sum of the inputs with shift rows included plus the sum of the outputs of mixed columns. Here's the non-triviality constraint. And finally, we need to set our optimization objective, so our cost function. And this is simply the sum of all active S boxes over all rounds, over all rows, over all columns. We solve, and tada, we get the result as the objective value. So this is the actual best possible cost. And we already know, or we can expect what this is going to be, because we already know that 4 rounds of AES have exactly 25 active S boxes, and this program here confirms it. So it will spit out 25 as the minimum number of active S boxes. And if you want to look what the corresponding solution looks like, you can do it like this. So this will simply print out a string representation of all the variables. You still need to match it back to the picture. Okay, so this is a short code example. You see it's easily written down. It just takes a few lines, and it confirms what we already know from theory. Namely, if we take any multiple of 4 rounds, we get exactly the corresponding multiple of 25 active S boxes, just as we expect from theory. However, we can of course also run this problem for round numbers that are not a multiple of 4. So for example, for 5 rounds, we can then see that instead of 25, we get 26 active S boxes. But if we only look at 3 rounds, we are already quickly down to only 9 active S boxes. So this is maybe nice to explore how the number of active S boxes grows over the number of rounds in AES. So we can of course make more interesting models out of this. AES is sort of the simplest thing that you can do. And one of the things that MILP problems are often used for is when you're looking at related key characteristics, where there may be some additional differences in the key. In this case, we need to change the description of add round key because we need to model the key schedule and we need to model the XOR. We're going to see a bit later how that works. And it turns out if you allow the attacker to introduce additional differences in the key, then you actually get a total lower number of active S boxes. And this is because you can, if you cleverly choose active cells in the key, you can use it to cancel out some of the active S boxes. And the good diffusion doesn't work as well anymore. However, it should be said that if you actually want to run an attack based on a related key characteristic, this usually doesn't work because people don't usually use related keys. Except in some maybe not so great situations, or as a building block, for example, for hash functions. And similar approaches to this are quite popular in new designs, and in particular in tweakable block ciphers. Because while related key attacks are maybe not so great, related tweak attacks are quite practical because the tweak is usually under the influence of the attacker. So a related tweak characteristic is something that is easily exploitable. And doing proofs by pen and paper is a lot harder in this related tweak scenario. So this is where MILP solvers are very useful. However, of course, not all ciphers are as simple as AES in this regard. So we're going to have a look at a few extensions to this MILP model that can be useful, or that are maybe a bit more challenging. So the first case that we're going to look at is if our cipher description doesn't just have the AES-like operations, but maybe some additional Boolean functions, such as a bitwise XOR, which we would get in the related tweak model. Or also, for example, if we're looking at a Feistel cipher, which uses maybe AES as a round function or so, the Feistel XOR would also need to be modeled in some way. Now, if you try to Google for Boolean operations in MILP, you will find many pages which tell you which give you some gadgets, how to translate particular Boolean expressions to linear constraints. So for example, if you have 2 variables and you want to model A or B, or something like A implies B, you can find suitable conditions. However, we don't really want to directly translate these Boolean expressions. Instead, we want to describe the behavior of differential patterns, which is not the same thing. So for example, if you look at an XOR, so you say you have 2 input cells, like bytes in case of AES, and 1 output that is computed as the XOR of these 2, which patterns are possible? Well, if both input differences are 0, then the output difference also has to be 0, because identical inputs, identical outputs. If one of the 2 inputs is active, then it still looks like the original XOR, so the output must also be active. However, this is actually not completely trivial, because each of these boxes here represents not just one bit, but one byte. But still it holds that if at least one bit is active in one of the two input bytes, then there must be a corresponding active bit in the output word. This is because if you add a pair of different values to a pair of identical constants, you still get a pair of different values. And the same is, of course, if you swap the order of the two. Now, where things get different from bitwise XOR is if both inputs are active. Because in that case, it could be that both outputs are inactive, because the differences in the input cancel out like they would for a standard XOR. However, it's also possible that the output is also active. Why is that? This is because if the input bytes are active, we aren't guaranteed that the active bit is in the same position. So it could be that in this byte here, the first bit is active, and in this byte here, the second bit is active, which means in the output, both the first and the second bit of the byte are going to be active. So it can be either this pattern or this pattern. And you can similarly think about this if the operation you're looking at is not XOR but AND, and maybe you can try to understand on your own why this is the correct description of the bitwise behavior of AND. Now the question is, of course, we have here something like a truth table. It's not exactly a truth table because it's not deterministic, so some inputs allow multiple possible outputs, but still we have a sort of some relation between the inputs and the outputs. It's not a function, but it's a relation. And this is something we can describe with constraints. So how do we do this? I will show two different ways here. The first one is useful for XOR, and this is because we can use a trick we already saw. We can use again this branch number modeling trick. So in case of mixed columns, we had the case that we had 4 cells at the input here, 4 cells at the output, and we knew that a total of at least 5 of them would need to be active, so a branch number of 5. Now if you look at this picture here, this is actually a linear function which has a branch number of 2, because there are either no active cells at all, or there are at least 2 in total. So either one input and then the output must be active, or if 2 at the input are active, the output may or may not be active. So this is actually precisely described as a function with branch number 2. So we could use the same model that we saw for mixed columns. We could use it here, except that we replace the 5 by a 2 and the 8 by a 3, because we have 3 cells here, and then we use the same model. We can also try, so this is something that won't work so well here, but we can still try to first express the relation between the output and the input in some clear way, for example, using a Boolean expression. And then we can try to translate this expression to MILP. So in this case here, if we look at this description, what we see here is that the output is only permitted to be active if at least one of the inputs is active. So in other words, output implies input 1 or input 2. If the output is active, then one of the inputs must be active. How can we describe this in integer equations? Well, what this means is that if this value here is 1, then this value here must also be 1. If this one is 0, we don't care. And we can write this as an equation like this. We can say that the output bit must be less or at most as large as the sum of the input bits. Now, as soon as one of the input bits is 1, the sum here is 1 or 2. And for this to be larger, O can be 1 or 0. However, if both of them are inactive, the sum here is 0, and the output must also be 0. So this linear expression here has exactly the same solutions as this Boolean expression here, and is thus a suitable model of this AND here. And the good news of this approach compared to this is, or the advantage is, that sometimes you can get away without introducing any helper variables. So here we would have to introduce an additional activity helper variable, like in mixed columns, which is of course bad because this is one more variable with an integer constraint which will slow down the solvers. So if we can do it this way, this is usually preferable. Okay, let's have a look at one more complex example. And this is ciphers which have a lightweight mixed columns matrix. So we saw that AS was perfectly described by its optimal branch number, but lightweight ciphers often have a less than optimal branch number, and they also often are not described completely by this branch number. So here is an alternative mixed columns matrix that you find in some ciphers, such as, for example, in Midori, which is a low energy cipher. And it simply computes each output of this mixed columns layer as the XOR of some of the corresponding input cells of the column. Now if we try to so this has a branch number of 4, so it's nearly MDS. However, if we try to describe this function by its branch number, we see that this is not quite identical. So here are 3 pictures. The first one of them shows the solutions we would allow based on this branch number, where solutions means I'm writing here all 16 possible input patterns, so where the pattern is a binary vector with 4 entries, written here short in hex notation, and this is the output pattern. So it's like a DDT, but it's for patterns and not for differences. And these are all transitions that satisfy the branch number of 4. However, we can already see that this is not a perfect description if instead we describe mixed columns by describing each of these XORs individually with the trick we saw on the previous slide. Then we suddenly get only fewer permitted values. However, if we draw a picture of all the possible pattern transitions that are actually possible, we see that it's even fewer than the XOR description here. So this is what we want to have, and if we just write down the branch number, this is what we get, which is way too many possible solutions. We could still use this if we're just interested in a bound, but it's going to be a lot less efficient. So what we need to do is we need to describe this table here in linear equations. And if we have a close look, we can see that the table has actually quite a peculiar structure. So there are so all of the possible transitions fall in one of these 4 categories. So either there are 0 active cells in total, or then we have 2 cases that exactly match the branch number, which have 4 active cells. And these are here on the diagonal and on the anti-diagonal. Now on the diagonal, these are exactly the patterns where the input is the same pattern as the output, and you will notice that they have exactly 2 active cells at the input and at the output, and those are in the same positions. So for example, input pattern 0011 goes to output pattern 0011. So the input and output pattern are identical in this green case here. And then there's the case with also 4 active cells, but where each bit at the input is the inverted bit at the output. So for example, the first line here, 0001 goes to 1110, or 0010 goes to 1101. So this is always the inverse, so to say, the additive inverse of this value here. These are on the anti-diagonal, and they have exactly 3 bits at the input and 1 at the output, or vice versa. So that in total it's still 4. And finally, the blue cases, these all happen to have exactly 6 or more active cells. So you will notice that there are actually no solutions with 5 active cells. There is simply no valid pattern. And now we can sort of try to describe these cases here. We will again first try to describe them in a Boolean description. So we can summarize the description of these 3 cases by saying that for each position in the column, so for each cell, the XOR of the input and the output pattern in this cell needs to be the same as the XOR of all input cells, which is 0 here and 1 here. And for this case here, we can use the same description as before. We simply say the sum of them all is at least 6. Okay, and what we now want to express is that either this or this must be the case. And this being the case means that this constraint must hold for each position I. So we actually have 4 constraints, C1 that this holds in the first position, C2 that it holds in the second position, and so on. So these 4 conditions correspond to this. And then we have, so either this is the case, all of them, or this condition here. And so we have again a Boolean expression that we want to translate to a linear equation. which means we're going to introduce a helper variable that represents whether each of these equations or conditions is true. So we have 4 helper variables, C0 to C4. And we can describe this one here by saying that the sum of all these here plus 4 times this second one here must be at least 4. Now this implies that either this is true, plus maybe some of them, or all 4 of them are true, which is exactly what we wanted. Now we need to still link these helper variables with the conditions here. And we do this for C4, that's easy. We do it similar as for mixed columns. We say that the sum needs to be at least 6 times this condition. So this condition can only be true if the sum is greater than 6. And for the other ones, these are XOR equations. So we can rearrange them a bit. We can say that BI XOR all of the AJs except for AI, because this appears on both sides and cancels out. So this sum needs to be 0. And we can write this, we can translate this by saying that the integer sum of BI and all the A's needs to be an even number. Because if it's an even number, then the XOR is 0. So XOR is simply computing modulo 2. So it needs to be an even number, 2 times x for some x. And now we allow this constraint to be either satisfied or not. And we do this by adding 1 minus the C0 here. So if it's an even number, then this one here can be 0, which means that the CI can be 1, meaning that the condition is satisfied. But if this condition here, it's not an even number, then we need this here to be 1. So we need this here to be 0. So again, we've linked the helper variable with this condition here, which describes exactly this one here. So by adding all of these conditions, we have now perfectly described this table, for example. Now, mixed columns is not the only case that gives us a table that we want to model. There are also other tables that we might want to model. In particular, if we look at ciphers where just describing the S-box patterns is not very useful. For example, in a cipher that isn't well aligned, or in a cipher that's, for example, an ARX cipher where the bitwise differences have a big impact. So if you look at 1 round or 1.5 rounds of present here, if we simply describe the possible transitions of S-box patterns, this wouldn't tell us anything about the cipher, because the patterns would simply be if some S-box is active, then at least one of the output bits needs to be active, which means at least one of the S-boxes here needs to be active. So we could get a simple pattern which simply allows the first S-box in each column. But this isn't useful for a bound, because for present, this would give us a way worse estimate than the truth. So this would be a case where we actually want to model the exact differential distribution table of this S-box here and have one decision variable, not for each byte or nibble, but for each bit. Now this is theoretically feasible, and you can, if you try to do it by hand, you can try to do some tricks like this. However, if the S-boxes are larger, and since they're usually more complex and not so well structured like this here, this becomes quite messy. There are some automated tools that automatically do what we did on the previous slide, namely translating such a table called vertex representation to inequalities, which is called half-space representation. However, these will, even for a small table, usually give you hundreds or thousands of equations, which makes it rather hard for the MILP solver to use. So while this is possible in theory, it's usually not a good idea. So instead, if we really need a bitwise model, you usually use another type of solver. So to summarize what we've heard about MILP solvers, these do solve an optimization problem. So it gives you a perfect optimal solution. It is useful and very easy to use if you apply it to only find patterns or bounds for so-called strongly aligned ciphers, which have an AES-like structure, because the MILP model is quite useful for evaluating the cost of these as a weighted sum of some of the variables, though we can also use something more complex. And it if we have so few variables in such a simple round description, then you can easily apply this tool even to the full number of rounds of these ciphers, which is very nice. The downside is, as soon as you have many more integer variables, because you're doing, for example, a bitwise description, or because you have a very large state, this usually becomes too inefficient for the solvers. So you get too many variables and thus bad performance. And the other thing is that you maybe figured out in the last few minutes that this language of linear inequalities is not really a very natural language to describe crypto, because crypto is usually very far from linear. So some good things, some downsides. Overall, MILP is still a very popular tool that is used quite a lot, both in cryptanalysis and in design. Very often for characteristics, but also for quite a number of other things. So it's definitely a very useful tool to have in your personal toolbox, whatever you want to do with it afterwards. Okay, so this would have been everything for the second method. Now, we're only going to look very briefly at the third method because it shares some similarities with MILP solvers. So the third method that I mainly want to mention but not describe in detail is the case of satisfiability solvers. And this actually comes in several different levels of convenience, I would say. So the very basic and classical approach, that is however usually not so convenient, is to use a SAT solver or satisfiability solver straight as is. So what does a SAT solver do? You probably know that. It finds a valid solution or proves the unsatisfiability of a formula given in conjunctive normal form. So it's written as an AND or a disjunction, conjunction of many ORs of literals, where each literal is either one of the Boolean variables that we are looking at as decision variables, or its negated form. So this is the format accepted as an input here. And of course, we know that this conjunctive normal form is quite powerful. It can express any set of Boolean constraints that we have. However, this translation process of some Boolean network or description or constraints into a CNF can be a bit painful. It can be done automatically, but the formulas often blow up massively. So you can do this, and there are a few implementations flying around on the internet that also do this for ciphers, for block ciphers, or at least for certain types of block ciphers, where you give a description of the cipher and it translates all of the round operations into such a conjunctive normal form and then tries to find a valid solution. The good side of using this right away is that there are a myriad of solvers that are fairly optimized that solve this kind of problem. I'm just mentioning here one very simple one, and one that is both quite efficient, which is why we've used it a lot, and it also happens to be from Austria, so from Linz to be precise. Yeah, so the good thing is many solvers available. The bad thing is the translation process can be a bit painful. The good news is that there are tools that do this translation for you in a very general way, so not crypto specific. And one of these is the family of SMT, or Satisfiability Modulo Theories solver, where modulo theories means you have a more general, more expressive language than just CNFs. So for example, this language allows also constraints specified in terms of bit vectors. In particular, it usually also supports things like integer addition. So you can describe constraints that are bit vector A is the sum of bit vector B and bit vector C, or something like that. And what these solvers usually do is they just automatically transform these Boolean descriptions here into CNF and then feed the result to a SAT solver. Of course, they do this in a clever way, and this is actually quite complex if you want to do it efficiently. But in the end, you essentially still use a SAT solver underneath. And one that is quite convenient for this purpose that we've already used quite often is STP, the Simple Theorem Prover, which has an easy to understand input language where you can write down your constraints in terms of integers, bit vectors, Boolean expressions, and so on, and it will translate it, and then you can plug it into your own SAT solver. There's also an even more generalized version of this, which is sometimes called constraint programming, but depending on where you exactly work in this field, you may not be happy with this categorization I give here, because some people see these as sort of the same thing, or this just is a very, very general term that covers everything and would even cover maybe MILP solvers and so on. That depends a bit on your viewpoint. So in any case, constraint programming is a very general term for a very, very general family of grammars. And in some cases, these solvers also translate what you're giving them into subproblems. And some popular solvers include Z3 and Choco. So I don't want to go into any of the modeling details, because you see there are many different languages to model in. There are many different tools to use them on, so just picking out one of them wouldn't really be very helpful. What I instead want to do is say a few words on the properties compared to MILP solving. So unlike the MILP solvers, here we're not looking at an optimization problem, but at a satisfiability problem. So you get one solution, but it may not be the optimal solution in any sense. In particular, because you don't usually have any sort of cost function. You can, of course, manually implement one, since you have things like integer addition. And you can also emulate things like optimization by starting multiple program runs and asking things like, is there a solution better than x or better than x plus 1, and so on and so on. But this is not necessarily efficient and only works in some cases. The good news is that one thing that SAT solvers or SMT solvers are very good at is, if you have already some idea about what your solution looks like, for example, you already have a pattern from a MILP solver, for example, and you want to find a valid solution, then this is something the SAT solvers are quite good at. So you describe the constraints of the characteristics in a similar way as we did for MILP, but in the SAT language. And additionally, you specify things like this byte must be active, so at least one of the bits must be active, and so on. Another good thing is that SAT solvers work quite straightforwardly for other crypto problems. So for example, pre-image problems. However, they are usually not very good at this. So of course, they're general purpose solvers. They don't have any domain-specific knowledge. So usually things like collision attacks or pre-image attacks can be done much faster if you use your crypto knowledge than by just writing it down as a SAT problem. Well, another positive point is that, well, it's for Boolean expressions, so crypto are usually Boolean circuits, so translating them works reasonably well. However, crypto is particularly fond of some operations like XORs, which actually don't look so nice in conjunctive normal form, so this is a bit of a downside. Another downside is, since this is a very general sort of solver, it's often not so efficient for more complex problems. So it often can't cover too many rounds because this would generate too many variables. And it's also often very painful to model a sort of cost function or optimization goal. So you see that this is sort of swapped around from the MILP case, where modeling the cost was easy, modeling many rounds was easy, but finding bitwise solutions was painful. And here it's sort of vice versa. So in other words, these two extend each other very well. So very often what you see is you first find a pattern using MILP, and then you find a solution for this pattern, a bitwise solution using SAT. But instead of looking into this in detail, we want to have a brief look at a sort of crypto-specific thing that works a bit like a SAT solver, but optimized specifically for crypto and for differential characteristics. And this is our method number 4, namely a dedicated guess and determine search tool. So guess and determine is quite a general attack strategy when you're trying to find a solution for some variables. What you do there is you fix some of the variables to some value. You see whether you can learn anything from it, whether this is a valid solution, and if yes, then you continue looking. So you traverse a sort of search tree. And if it doesn't work, then you go back and try a different value. This is essentially the same sort of structure that you do find in SAT solvers, where the things like the guessing strategy and the propagation are done on the level of CNFs. But what we are going to look at in the following example is one that works on a sort of more general grammar, where the description level is not a CNF, but differential circuits, but where the text or the general search strategy is related. And there are, I think there are several places where similar strategies are implemented, but I want to focus on a particular example which was developed at the institute at IAK, specifically for differential challenges, and in particular it was implemented for finding hash collisions. And the most relevant application example for this tool where it has been used is SHA-2, for which it's currently the source of the best known practical collision attacks, of course on round reduced versions. So SHA has a very, very large security margin, but this is sort of the best tool we have to find collisions for round reduced variants. So what we're looking for is we have a compression function where the input is larger than the output. We feed something with a difference in, and now, unlike in the previous cases, here there can actually be collisions because the input is larger than the output, and we're looking for some input difference and later also the corresponding value such that the output difference is 0. So that is the goal, and the method is going to be this general structure here. So first, a few words about the difference notion that we're using in there, because it's going to be a bit different from what we saw before. Before we always had this this binary decision, so in each variable we had either a 0 or a 1, which means there is a difference or there is no difference. But here we're going to look at a more refined representation, and this is because we are trying to I'm coming to that in a moment. So in any case, the first motivation to use a different sort of difference notion is the fact that SHA-2 is an example of an ARX design, which means it doesn't just have S boxes and XORs, but it uses modular addition of words as well as the XOR of words. Now, if we're looking at XORs, then the XOR difference is a very natural thing to look at. So where the difference is simply the XOR of the two values. But if we are looking at modular addition, this is no longer the case. Here we would be more interested in the modular difference, which is the first v-bit vector minus the second v-bit vector modulo 2 to the word size. And so we want to use a difference notion which is useful both to describe modular additions and XORs. And a sort of compromise is the so-called signed difference. So what the signed difference says is for one bit, it's either 0, +1 or -1, where a signed difference of 1 means the same as a difference of 1, so the both bits are identical. But if there is a difference, we actually distinguish the two cases, +1 and -1, where +1 means the first bit minus the second bit is 1. So in other words, the first bit is 1 and the second bit is 0. Or vice versa, the first bit is 0 and the second bit is 1. So instead of two cases, difference or no difference, we now have three cases, which are either no difference, or the pair is 0, 1, or the pair is 1, 0. And the reason why this is attractive is because if we fix a signed difference, this determines both the modular difference between the two words and the XOR difference. So for the XOR difference, this is clear. A signed difference of 1 means an XOR difference of 0. And a signed difference of plus or minus 1 means an XOR difference of 1. So if you take the absolute value of the signed difference, you get the XOR difference. And for the modular difference, you use these here as exponents for 2. So you're summing powers of 2, and this gives you the exponent. And then you get exactly the modular difference of the two values, modulo 2 to the power of the word size. Okay, so I think there's a typo here. I need to fix that afterwards. Sorry. But yeah, so this is why we're using where we're starting to think about sign difference, but actually we're not staying with sign difference. We want to add or to achieve an additional goal, and that is to represent the entire search progress in our difference notion. So we're searching starting from something where we know nothing about each bit, and then we gradually refine it. So we add some knowledge to each bit. And we want to represent this full progress with our difference notion, which is why we use so-called generalized differences, where the generalized difference of a pair of bits can be one of 16 possible values, and each of these corresponds to one possible subset of all the possible values of this bit pair. So for example, the generalized difference that we denote by 0 means that out of these 4 possible values of our target bit pair, only one, namely the last, so 0, 0 is possible. So 1 logically means both bits are 0. 1 means both bits are 1. U and N mean either the first is 0 and the second is 1, or vice versa. But we can also represent things like our classical differences, like the two are either 0, 0 or 1, 1, so they are equal. Or they're either 1, 0 or 0, 1, so they're different, and so on. We can also model things like we have a contradiction, or we know nothing at all, so any value is possible, and all the other combinations. So we're going to start with a state that we describe mostly as question marks, where we know nothing. And then we try to gradually refine them to have fewer and fewer options, and at the end we want that all bits are fixed to one of these values here. So we know precisely what the values of both involved bits are. So this is our search strategy. And how do we do the search? This is where the name comes from, guess and determine. So we iteratively do the following. As long as there are still undetermined bits, undetermined meaning it's not part of this set here or whatever we want to find, then we pick one bit that is still undetermined and put a constraint on it. So we reduce and take away some of the possible options. What exactly we do and what we guess, this is then defined by the detailed search strategy, but what we definitely do is we remove some options, and then we see if we can propagate or deduce anything from this. So by removing some options for one bit, can we also remove some options from other bits? If this works out well and if we don't find a problem, we continue, we take the next bit and so on. However, if we find a problem, because the constraint that we added actually led to a contradiction in some place, then this means that one of our previous guesses must have been mistaken. So we undo them step by step. So we start, for example, by undoing the last guess and trying if the opposite works. If not, we need to go further back and so on. And we keep doing this. So in other words, we keep walking around our search tree until every bit is fully determined. Now, how do we propagate this information? So how does this step work to check if constraining one bit also constrains another bit? For this, we first need to represent our cryptographic circuits suitably. And we do this by dividing it into a number of so-called bit slices, where a bit slice is a part of the circuit that involves some of the bits and where we can give a reasonable Boolean description of what's going on. So for example, if we have a linear layer with some input variables and some output variables, where each output variable is computed in some way from the input variables, then as an XOR of some of them, then one logical choice of bit slices would be this one here. So one bit slice covers this output bit and all corresponding input bits, the same for the next one and so on. Now these individual bit slices are going to overlap a bit, of course, but still if we describe all the individual functions, we have completely described the full function here. Or for example, if the function we're looking at is a modular addition, then we can simply model each bit of this modular addition by saying that each bit of the output word is the XOR of 2 bits of the corresponding 2 input bits and some carry. And of course, for the carry, we also need to give a formula that depends on the previous carries and the current previous values. So we can decompose a more complex or an operation that has many bits into smaller slices that have fewer bits, but that still completely describe the cipher. And once we have done this, we can now propagate each of these bit slices. So for example, if we look at just a single XOR where the output bit is computed as the XOR of two input bits, and assume we have some previous knowledge of these bits. So for example, about the first input bit we know nothing, but the second we know that there is a difference between the pair, and for the output we know that the two output bits are identical between the two runs. Or in short, we say that for this 3-bit bit slice we have these 3 conditions. Now what does this mean? This means that for the combination of these 3 bits here, there are a total of 16 possible 6-bit combinations for the 3 bits in the one execution of the cipher and the 3 bits in the other cipher, and they're all listed here. And this is based on this description here. So this is always 4 options for the first, times 2 for the second, times 2 for the third bit. So in total 16 options are possible. However, if we now go through all of these possible bit assignments and check whether they are actually compatible with our function here, so whether in each of these cases the corresponding output bit is actually the XOR of the two input bits, we see that there are many contradictions. So for example here, 0 is definitely not the XOR of 1 and 0. So this is not a valid value. It's permitted by this condition here, but it's actually not valid. So if we look only which of them are valid, we only get these 4 possible combinations. And we now see that we can describe these 4 possible combinations in a stricter generalized condition than this one here. So in particular, we notice that in all of these cases, the first 2 input bits are actually different. This was not in the original description, but actually in all valid solutions, this is the case. So sorry, these 2, not the first 2 here, so none, but this and this and this and this and so on. So this means that we can describe these cases here with a stricter generalized condition, namely XX dash, meaning the first pair is always different, the second pair is always different, and the third pair is always equal. So we have propagated from this to this by simply enumerating all possible solutions and checking whether there is a stricter description of this than we had. So this is bit-sliced propagation, and can be implemented efficiently as long as enumerating all these options here is efficient, which means there shouldn't be too many bits involved in one bit slice. So something like 3 or 4 or 5 is fine, but something like 20 is not fine. There are of course other ways to propagate, so in particular when we know something more about the cipher, but this is the most general and useful approach that can be used by itself. Now we do know how to propagate, so we now need to still somehow illustrate what our search looks like. So we start from something where many things are undefined, and then we gradually pick some of the undefined bits, impose a stricter condition, such as, for example, we say that the x0 is here, needs to be an equal bit, and then we keep going. And whenever we run into a contradiction, which means if we run into the case that none of the remaining solutions is actually valid, then we need to go back to backtrack and then always try the alternative option. So for example, if setting the 2 bits to equal didn't work, then alternatively we need to set them to a difference and keep going and so on. So as an example illustration, let's look at SHA-2, which in general is just such a compression function as we saw, with an input consisting of in case of SHA-256, a 256-bit chaining value, a 512-bit message, and producing a 256-bit hash value, or the same thing in twice the size for SHA-512. And what I've illustrated here is that what the internals look like. So internally, this message here, which is here in red, is expanded. So it's like a key schedule, but it's a message schedule. It's expanded to message words. And the input chaining value is updated in 64 steps by some function. And in each function, we XOR or we add one of these expanded message words to the state. So it's a bit like it's a block cipher. This one is the main state and this one here is the key schedule. At the end, there happens to be an XOR, but we don't care about the details. In any case, the structure is the same for both. And the round function that is applied here to these 8 words, so the 8 32-bit words or 8 64-bit words of the state here, is the following. So it's a generalized Feistel construction where actually only 2 of the output words are actually computed in a complex way from the inputs by using some functions, whereas the other 6 words are actually just shifted copies of other words of the state, rotated copies. So like in a Feistel, except that the Feistel here updates 2 values instead of just 1. And here we also see that the message word, so from a message schedule, is added at some point. Now, the good thing about this description is that it can be, since only 2 words are actually updated, it can be represented more compactly in an alternative representation, where we only write down in each step the current value of the message word. So that's this one here. And the current value of A and E, where A and E are those 2 words of the state that are actually updated. And these are updated based on the previous A, B, C, and D. Now, since each of these are just shifted copies of the old A's, this means that, in other words, at one step, the A word is updated based on the 4 previous A words and the current E word, if you look at this function here. So here's the E word, and here are the previous A words. And the same thing for E. So E is updated based on the 4 previous E words and a very old A word and the current expanded message word. So you can see this if you follow the lines here. And finally, the message expansion is very simple. So it simply computes 1 word here. So the new thing is always marked in red. Computes it from some of the previous message words. And the first few message words are simply a copy of the message. So this is what the state update looks like. And we now can represent the characteristics using the following sort of illustration. So we're showing here, if you see here the compression function with a message input and a chaining value input, which produces some output. We're representing it like this. So we have these A and E words, which are initialized, if you saw it in the previous picture, they are initialized from the IV input. Then we have here the W, which is the message words, which are initialized from the message, and all the following words are then computed recursively from this. And all the A and E words here, so 1 line for each step, they're also computed from the previous A or E word and some of the older ones. And the final output is going to be in the final 4 A and E words. So that's the output here. So this is the picture we use. And in this we can now try to apply our guess and determine search. For this we first need to have a general description of what we are looking for. So we want something that collides at the end. So which means at the end here somewhere we want to have a state starting with all 0 differences. And before that, somewhere there need to be differences. So these differences can be introduced in the message. We only want a so-called semi-free start collision, which means we want no differences in here. But we do allow differences here. And these will then, since the later words are computed recursively from this, there will also be some differences in the words here. And we need to choose them in such a way that they are able to cancel out the intermediate differences here. So to make it a bit clearer, what we want to build is a so-called local collision, where we have some message words here, which allow some later words to be derived, but we want to choose them in a clever way, such that in some of these computations, so in the gray ones here, these would usually be computed from 2 or 3 or 4 orange values. However, we want to choose the orange values in a clever way such that the differences cancel out and we get no difference here. So white and gray means there is no difference. Gray in particular means that there could be a difference, but it should cancel out. And orange means that there is a difference potentially. So this is for the message part. And if we look at the state words, since we know that, for example, this value here is computed from this orange value and some previous values, at least one of them needs to be orange, we can try to choose this orange word and this orange word in such a way that they also cancel out here. So we want this plus this to cancel out that part here. We want this plus this to cancel out this part here. And we want the message words chosen cleverly such that this cancels out here. And then we have identical values here and a collision in the end. Notice that this is round reduced. Usually there would be more rounds here. However, the next round here would be one where only one orange word would be involved, which means we would get a difference again here and our collision would stop working, which is why we have to stop at this point. So this is a sort of starting point that we can find by hand and that we can describe as initial constraints to our solving problem. And then we can start using this guess and determine search by picking some of the bits that are still open here, which means essentially anything, and try to guess it to something useful. So what we usually want to do in the beginning is there are some parts where we want to have only very few active bits, in particular here and here, to make sure these cancellations work out well. So we should maybe start guessing there. And in particular, we want to start guessing them in such a way that there are almost no bits which are active. So only very few differences. So if we do this, for example, we can start by refining the question marks to X's and dashes, so to difference or no difference. And we do this first in the parts where it's important. And then we can, if we found something that works here with very few differences, we can continue going in the denser parts here. And to do this, what we want to do is we want to find what we said earlier, what we called earlier signed characteristics. So each of these red bits here means we have fixed the signed characteristic to either +1 or -1, which means from this red pattern here, we already know the modular differences, which is relevant because there are many modular additions in the state update function. But it also allows us to evaluate some of the Boolean stuff. And the parts that are marked gray here now, these are parts where there is no difference, but where the specific values that we know in the red stuff actually implies some specific values for the bits. So either 0, 0 or 1, 1. And you can see here that there are already many conditions. So this part here is already mostly determined. There are many more differences here than in the part where we paid attention to a few differences. So this is part of the search strategy. And we can now continue doing this and continue finding the missing white bits, which are not fully determined yet, piece by piece in some particular strategy. And when we have completely done this, we can choose the remaining white stuff here and hope that it satisfies the remaining parts here until we have a fully determined state. So we keep doing this guess and determine stuff until everything here is gray or red, where red is either 1, 0 or 0, 1, and gray is either 0, 0 or 1, 1, but we know which one of them. And when we've done this, when we've found a valid solution that doesn't lead to any contradictions anymore in our guess and determine strategy, then we've found a valid collision. Okay, so we found which message we need to use, which has a difference in some bits, and we've found a valid IV. No? Are you not interested in tools for cryptanalysis, kid? Huh? We're almost done anyways. So what are some improvements that we can do from this basic starting point? Well, there are many things where I haven't described the strategy in detail. So how do we find the starting points? What is the best way to find a good representation of bit slices? How do we decide which variables to pick first in our branch, in our search tree? This, of course, makes a huge difference. How do we determine contradictions and so on? So there are many, many things where a detailed strategy is necessary and has a lot of influence on the performance of the result. We also need to decide how far to go back when we go back, whether we restart at some point and throw everything away we've done so far because we've grown frustrated with it, and so on. So there are tons of places to optimize this. Okay, so that's it for the overview of the 4 methods today. Actually, I haven't written a conclusion. I've just copied the table of contents again to summarize briefly what we've looked at. So we've seen 4 rather different methods for searching for characteristics, from some general recursive strategies that work mostly only for lightweight ciphers or Feistel ciphers, to some that work well for AES-like designs where we can search for patterns, to some that are good with bitwise descriptions, but only if we already know something about the solution. And finally, we've seen one that works well also for bitwise descriptions, but where you can, as a cryptographer, add quite some of your domain knowledge to the search process, because you write the search procedure, so you can write things like where to guess first, which values to guess preferably, and so on. So 4 different tools for 4 different scenarios that appear when searching for characteristics. I hope that you will find an opportunity to reuse some of them in whatever you are doing in the future, whether it's cryptanalysis or other stuff. So in particular, these 2 here are quite useful, and I could imagine they also have nice applications if you're partially staying in crypto doing something like sidechain attacks or so. But also they are very useful tools in general that are good to have in your toolbox. And you may also have to use one of those for the exercises, but we haven't fixed that yet in detail. Okay, so that's it from my part for the lecture. If you still have any questions, of course the chat is open. I haven't seen anything yet today there, so maybe you just say hello to me. That's also nice. If there are still any last minute questions or issues or problems that you have with the exercises, or if you have some problems with the submission or so, you can also quickly drop me a message in the chat, where if necessary we can also still open the video chat from last time again, but since I haven't seen anything yet, I guess that won't be necessary, so I'll just stay here a minute longer or so. I'm happy if you leave me any comments. I'd also be very happy if you leave us some comments at the end of the term in the evaluation about what of this worked and what of this didn't work so well. But in the meantime, good luck with the final submission of the exercises, and yeah, I hope you're ready for the new exercises starting next week. Sorry for the lack of cat content today, by the way. She wasn't motivated. So there was one question on the exercises about how to submit each task. You will notice that there are many tick boxes for each subtask. It's not necessary to upload a separate file for each of them. So one thing that could work well if for each of the 3 large tasks, if you have one solution that does everything, you can just upload the same file to each of them. So as long as you tick each exercise that you solved, and as long as some file that actually solves them is available somewhere there, we will find out. If you do happen to have separate files for each of the separate tasks, so for example in the factoring task, if you have separate implementations of the quadratic sieve and the basic random square algorithm, you can also upload them separately to the corresponding subtasks. but we are not too picky in this. So as long as we can find the solution somewhere, and hopefully your README tells us where, we're fine with it. And also please check that you actually ticked each one that you think you solved. If something goes wrong there, we may be able to fix it, but it will make the Abgabegespräche more complicated if your ticks don't match what you say you solved. Yes, so uploading one file to the first subtask is a good solution. Okay, then thanks for the questions and have a nice evening. Good luck with the submission and see you next week.